let's talk about the very center of the Fourier space, which is called the DC component, or the direct current component, because of an analogy to direct current electrical current. We generally, as we'll see in the next lesson, shift the origin from the corners to the center in the magnitude spectrum. So this point corresponds to u equals 0, v equals 0. And because natural images contain far more smooth regions, as we saw in the cat image, than abrupt transitions, the magnitude spectrum is typically brightest around the center, that is the low frequencies, and gradually darkens as we go more peripherally. And this represents the central portions of the image represent the smoother, lower frequencies, and the more peripheral regions of the frequency spectrum represent the fine details, the edges, and the texture of the image. The DC component again has a frequency of 0, meaning that it does not vary across space, either in horizontal or vertical dimension. It's the very center point of the image. The DC component also represents the average intensity or mean brightness of the image, and it's easiest to understand this by just looking at the Fourier formula. This is the formula. In many contexts, we scale or normalize the formula by dividing this double summation by the number of pixels. Now, look what happens if you look at the Fourier index at u equals 0, v equals 0. Well, this exponent becomes 0. E to the 0 is 1. So this formula is transformed to this. This is just the sum of all pixel intensities divided by the number of pixels. That becomes the average pixel intensity or average brightness of the image. So every image has a central bright spot right in the center of it, which represents its mean or average intensity, and if it's not scaled, it represents the sum of all pixel intensities. But that's not important. What's important is what's around it, the low frequency regions around the DC component and the higher frequency regions more peripherally. So now we're going to look at some simple examples to develop some intuition for how to interpret these frequency spectra. Here I have created a grid, or actually a grading, that varies in the horizontal dimension. In the accompanying Colab notebook, you'll see that I did this by using a cosine function, and I gave it a horizontal frequency of 4. So you can see 1, 2, 3, 4 variations within this image, and I gave it a vertical frequency of 0, so you can see there's no variation along the vertical orientation. So this is the actual image in the spatial domain. What happens when we take its Fourier transform? Well, you will have the DC component always, which is the point right at the center, and we can just ignore that. And then you will see a point to the right of it and a point to the left of it. Let's just consider one of these points. To the right of it is a certain number of u values away from this. It turns out that the distance from the DC component to this point is exactly 4 if I had numbers on this image. So that corresponds to a u of 4, a horizontal frequency of 4, which is in fact what I used to create this image. You can see there are no points up here. There are no bright points up here or down here because this image has a vertical frequency of 0. And again, the reason we have 2 points, one to the right of DC, one to the left of DC, is because the 2D Fourier transform is symmetric across both the U and V axes, and we always see mirror spots, and we only need to consider one of these two bright spots. So what happens if I increase the frequency? Again, you can refer to your Colab notebook and play around with this. Here we have increased the horizontal frequency to 40, vertical frequency is still 0. Well, then you can see that the bright spot moves away from the DC component. The distance from here to here is now 40. So U from 0 to 40 corresponds to this. Again, no vertical frequency. And as you might imagine, if I create an image with a vertical frequency shown here, vertical spatial frequency, the corresponding Fourier transform has a bright spot that is, in this case, 20 units away from DC. So in this case, V equals 20, U equals 0, corresponding to our spatial frequencies in the image. Let's keep going. What if I create an image that has both horizontal frequency, in this case 10, and a vertical frequency 20? Well, I get these oblique repeating patterns. And in this case, again, I get two bright spots here. Let's look at this. Remember, this is positive U and positive V. So in this case, I go 10 units to the right, U equals 10, and I go 20 units down with V equals 20. I end up with this point corresponding to a horizontal frequency of 10, vertical frequency of 20, which is exactly what I have used to create my image. And of course, I have its mirror in the negative frequency domain. What happens if I have a skinny rectangle over here? This is kind of interesting. So we have two very long edges where a lot of pixels experience rapid transitions in their gradient, and two short edges where fewer pixels correspond rapid transitions in their gradients. In the case of the long edges, the transition in pixel intensity is in the vertical orientation. So as a result, we have a very sharp and bright vertical line corresponding to all these transitions. And in the case of these vertical edges, we have fewer pixels that experience a horizontal transition. So we have a fuzzier, less focused beam going across the horizontal dimension. But you also see a lot of ripples in this image, and this is a special case because this image is considered to be finite and rectangular, so it creates, because of the mathematics of Fourier transform, it creates these periodic patterns both in the horizontal and vertical dimension, which we don't need to really think about very much. What if you have an image like this truck that has very strong horizontal, vertical, and oblique edges, where for all the horizontal edges you get strong transitions in vertical frequency, for all the vertical edges you get strong transitions in horizontal frequency, and for the oblique edges you get transitions in an orientation in the Fourier space that's basically perpendicular to the edge orientation in the spatial domain. If you have an image that doesn't have much very strong edges, then you end up with a kind of a uniform blob of bright pixels around the DC components without any streaking. If you have a picture that doesn't have very bright or well-defined edges but has a lot of texture, you get both. You get both a blob of pixel intensities around the DC component, and you also get some high frequency changes that capture the texture. So edges we saw with the truck produce high frequency. A lot of texture produces a high frequency. What if we have noise? Here I have used I've created synthetic noise using NumPy's random function, and this is the actual plot of the noise created in the spatial domain. If I take its Fourier transform, it's still noise. So the Fourier transform of noise is noise, and that's the only instance when we do not have a DC component because there's no uniform background. So in summary, and this is all I will need you to take away from this lesson, low spatial frequencies appear near the center in the magnitude spectrum, and they correspond to how much the image have smooth regions with gradual transitions. High spatial frequency occurs in the periphery of the magnitude spectrum, and it corresponds to how much the image has fine details, textures, sharp edges, and noise.